What's up, everyone? Today we're going to graph two more types of polar graphs known as rose graphs and Lymnus Gates, both of which have very similar properties to one another. Okay, so we'll start with rose graphs. The reason they're called that is because when you graph them, they will look like flowers. All right, and their equations will follow the form r equals a times cosine of n theta, where a is a real number and then n has to be a value of 2 or larger, okay? Let's give you some illustrations of these in Desmos before we begin our examples, okay? So here I have the equation r equals a cosine of b theta. So notice I'm using the letter b rather than n, no big deal there. And I have it so that a equals 4 right now, b equals 2. So let's adjust the value of a so you can see how that affects the graph here. Right now, notice I've got a flower that's got 4 petals to it. And you can see that this value of a just affects how large those petals are, the length of each petal. So right now I have a equals 5. You can notice that each petal has a length of 5 units. All right, what about B? Okay, well, B, you can see affects how many petals there are. So notice when B is 2, there's 4 petals. When B is 3, there's 3 petals. When B is 4, there's 8 petals. When B is 5, there are 5 petals. So hopefully you're noticing a pattern here. When that value is an odd number, that will tell you the number of petals you have. So 5 is odd, you have 5 petals. But if that value is even, then you have double the number of petals. So B value of 4 gives you 8 petals. Okay? All right, let's formalize this in our notes. All right, so notice, again, we're using the letter N rather than B in our notes. So we just observed that if that number is an odd number, then that's how many petals the graph is going to have. It's going to have N petals. But if that's an even number, we have to double that to tell us how many petals we're going to have. So that would be 2N. And we saw that the petals are all going to have a length of a unit. So whatever the value is, multiplying sine or cosine, that tells you your length. Now, one other thing you maybe were observing on your own is that all of your petals are equidistant from one another. So if I go back here, you notice that those 8 petals are all the same distance apart from one another. Okay, so that's very helpful to know when we go to graph these ourselves. All right, so let's graph r equals 2 cosine of 3 theta by hand. Here the n value is 3. That's an odd number, so that tells me the number of petals is 3. And then the length of each petal is going to be the a value of 2 units. Okay? All right, now notice below the grid here, I have a very important note. It says when graphing a rose involving cosine of theta, you're always going to put your first leaf on the positive polar axis. Now, the positive polar axis means theta equals 0 degrees or 0 radians. The reason we can make that statement is because cosine of 0 is as large of a value as you can get for the cosine function. Okay, so this is going to give you the furthest point away from the pole that you can possibly get. Okay, so in this case, notice I've already got a table made here. When I plug in 0 for theta, I end up with an r value of 2. So let's plot that point. Okay, and then you'll notice the next point that, or the next value for theta that I choose to plug in is 15 degrees. So that leads me to an r value of approximately 1.4, okay, which would place me right about there. And the other thing I should mention is our symmetry rules that we learned the last couple days, they still apply. So if this is a cosine equation, then I'm going to have symmetry in this graph with the polar axis. Okay, so that point that I just plotted of 1.415 degrees, I can reflect that across the polar axis, and that'll give me another point here. Okay. Next thing to plug in would just be 30 degrees. Notice that gives me an R value of 0. Okay. And those 4 points are enough for me to see that my first petal looks like this. Okay. All right, from there, I'm just going to use the fact that my petals are all supposed to be equidistant apart from each other. And I know that there's 3 petals, right? So there's 360 degrees in a complete circle. If I divide that by the 3 petals I'm supposed to have, that gives me 120 degrees. Okay? So if I place my first petal at 0 degrees, then my next petal has to be placed at 120 degrees, okay, which would put me right here. That's the furthest point of the second petal from the pole. And then I can just use the orientation of the other points from the first petal to give me my second petal. So here would be petal 2. All right, next, if I go from 120 degrees, another 120 degrees, that'll put me at 240, which places my third petal right there. You can also have gotten that using your symmetry rules and copy the orientation of the rest of the points from petals 1 and 2. And there you have it. There is your final rose graph. Okay, second example. Here I have the n value as 2. Since that's even, my number of petals is going to be double that, 4. And the length of each petal this time is going to be, notice the a values changed to 3. Okay. Now also notice this equation has sine within it. R equals 3 sine of 2 theta. So whenever I'm graphing a rose involving sine, I always put my first petal on the angle of pi over 2 divided by n. Or if you're working in degrees, that would be 90 degrees divided by n. The reason for that is sine will yield its largest value at 90 degrees. And here, if I have an n value of 2, the calculation 90 degrees divided by 2 will tell me what value to plug in for theta to give me that largest value possible. Okay, so notice I'm getting 45 degrees when I do that. And you can see that this is the first value that I've plugged in for theta in my table. Okay, so think about it. If you plug 45 into the equation, first thing that's going to happen to it is it's going to get doubled to 90. You find sine of 90, which is 1, then you multiply it by the 3 out front, gives you an R value of 3. Okay, so let's plot that corresponding point right here. All right, now notice the next value I chose to plug in for theta is just 30 degrees, so that's the angle directly below 45 in the grid. That gives me 2.6. And you can see that if I chose 60 degrees for theta, I also get 2.6. So that's just showing their symmetry within the petal itself. Then I just keep branching further away from that first point that I plotted. So if I use 15 degrees, that gives me 1.5 for R. And if I use 75 degrees, if I went in the other direction, 1.5 for R as well. And then finally, notice if I plug in 90 degrees, I end up with R equaling 0. Okay. So those 6 points can make my first petal here. Okay, now I employ the fact that the petals are equidistant apart from each other, so 360 degrees in the full circle. If I divide that by 4 petals, that's going to give me 90 degrees. So notice I place my very first point for the first petal at 45 degrees. That means if I rotate from there 90 more degrees, my second petal, its first point should be placed at 135, which is right here. And then you can just copy the orientation of the rest of the points from petal 1 to give you petal 2. All right, after 135 degrees, if I rotate 90 more, that puts me at 225. And I would place my next petal right here, copy the orientation of the rest of the points from the previous petals. And last petal will be placed at 315 degrees. All right. Notice we do have symmetry in this graph. There's symmetry in a lot of places, but the one I want to draw your attention to is we have symmetry with theta equals pi over 2, which is consistent with our equations involving sine from the previous couple days. Okay. All right. Now we move to the Lymnus Gates. Now, Lymnus Gates, again, their properties, you'll see some of them are similar with the Rose graphs. The equations will have to follow the format of r squared equals a squared sine of 2 theta or cosine of 2 theta. So a couple things I want to draw your attention to. Notice that both r and a are being squared here, okay? And then your n value for a Lymnus gate always has to be a 2, okay? No matter what. If it's not a 2, then this wouldn't graph to be a Lymnus gate, okay? These are going to graph to look like propellers, and sometimes they're referred to as ribbons. Lymnus gate is actually Greek for ribbon, and you'll see more of why that is named that way once we get the graph here, okay? So let's graph r squared equals 4 sine of 2 theta. Now, if you're doing this yourself, to come up with values for r, understand that you're going to have to square root both sides of the equation. So when I make this table that you see here, I'm actually using this version of the equation, okay? And notice I just plugged in all my first quadrant angles for this particular table, okay? 0 through 90 degrees in 15-degree increments, okay? So notice plugging 0 in gives me an r value of 0, so I've got a point at the pole. 15 degrees gives me an r value of 1.4. 30 degrees gives me 1.9. 45 degrees gives me 2. 60 degrees also gives me 1.9. 75 gives me 1.4, just like 15 did. And then 90 degrees gives me 0. So right there, all those points give you 1/2 of the Lymnus gate. And one thing I do want to draw your attention to is notice where the furthest point is away from the pole. It's right here at 45 degrees, comma 2. And notice that angle measure is 45 degrees, which is consistent with, if we go back to our Rose graphs, it's consistent with this property that when you're working with sine of theta, you're always going to place your first petal at 90 degrees divided by n. Well, in this case, the n value is 2, so 90 degrees divided by 2 is 45, okay? So just wanted to show you that similarity with the rows equation. All right, now if you were to plug in numbers between 90 degrees and 180, or any other angles that are in quadrants 2, 3, and 4, you'll end up seeing the orientation for the rest of this graph would be as follows. Okay, there's symmetry with the pole, actually. So we'll end up with our another furthest point away from the pole would be actually at 225 degrees. Okay, and then all of my other points can be found with the same orientation as the first half of this graph. Oops, plotted those wrong. There we go. And that would be the finish to your Lymnus Gate. So notice there is symmetry with the pole. Probably should have written that out earlier. Okay, all Lymnus Gates have symmetry with the pole. Notice this doesn't follow the symmetry rule from back here earlier in the lesson. Sine graphs, we've said, have had symmetry with theta equals pi over 2, but that's only in the case of r equals. Now that we have r squared equals, we no longer have that symmetry with pi over 2. The symmetry changes to being with the pole. Okay. Now, one last thing to draw your attention to, the reason these are called Lymnus Gates is because if you were to trace this out from an angle measure of 0 all the way rotating through an angle measure of 360 degrees, this is what the sketch would look like. It would start at the pole, come through here, and then we'd rotate around. So notice it's kind of like, as I sketch that out, it's kind of like tying a ribbon or tying, a knot in place. Okay. Had this equation been r squared equals 4 cosine of 2 theta, the only difference is you'll still have symmetry with the pole, but you would place your first point, instead of at 45 degrees 2, it would now be at 0 degrees 2, which is consistent with our rows graphs as well involving cosine. Okay.